Today I would like to talk about a spectral problem for higher order elliptic operator. More precisely, I am interested on stability estimate for Biharmonic operator. So let me begin with a brief introduction. To begin, let's start with a simple idea. So every physical object, whether it is a drum, string, or even Earth itself, has its own natural vibration. These vibration correspond to certain frequencies or spectral data. So the advanced spectral problem asks the following question: if we know how something vibrates, its spectrum, can we determine what it's made of or what shape it has? So, for example, we consider here the Sturm-Liouville problem in one dimension. So, with here the potential here is a real valued potential. So, one might ask is, can we determine the potential Q from the eigenvalues of LQ denoted by lambda K? But in general, these eigenvalues don't uniquely determine Q. So the first result of this direction was obtained by Absaromian, who showed that if the eigenvalues are equal to kk squared, so q equals to 0. After that, Sirov and Leversons showed that a single spectrum data is not sufficient to determine q, and they proved that if we have if for two different potential Q1 and Q2, if their eigenvalues and the Neumann data of the corresponding eigenfunction at the 8 point are equals, so Q1 equals to Q2, and this is known as the classical Bock-Leveson theorem. So in this work, we will extend this theorem to multi-dimensional elliptic operator. So let omega be a bounded simply connected domain of Rn. Here n is at least equal to. We consider the following operator, whose principal part is the perturbed Biharmonic operator, and include the first order perturbation given by a vector field B, and the zeroth order perturbation given by the divergence of B and the potential Q. Here the domain of H is equals to X. So this operator has a self-adjoint extension, so its the spectrum made of the sequences of the eigenvalues lambda k, and we denote by phi k the corresponding eigenfunction. We will find the following boundary spectral data as the sequences of all the eigenpairs, lambda k, and Neumann data of phi k, with Neumann data is given like this. So the inverse spectral problem we address here is, given the following boundary spectral data, can we determine the vector field B and the potential Q? This inverse problem was first studied by Kratos and by Valenta, who proved that for higher order elliptic operator with a potential Q, if we have the full knowledge of the eigenpairs, then we have the uniqueness. Moreover, they proved that for P is polyharmonic operator, if we have a finite number of measurements is missing, we still have the uniqueness. After that, Cyril considered the Biharmonic operator with second order perturbation, and he proved that if we have the knowledge of the second order perturbation and the first order perturbation on the boundary, and if we have the knowledge of the eigenpairs, then we have the uniqueness. Now for the stability estimate, there is only one result given by Owens half, who showed that for Biharmonic operator with potential Q, if we have the full knowledge of the eigenpairs, and if Q1 minus Q2 is in each 01 of the ball of radius R, so Q1 and Q2 are stably recoupled by the max of lambda 1 minus lambda 2 and by the following series of the Neumann data of the corresponding eigenfunction. So here n is arbitrarily chosen, but it must be finite. So natural question to ask what happens when n goes to plus infinity. And to ask this question is to ask whether there is an asymptotic behavior of the boundary spectral data. In fact, with the assumption we make on B and Q, we can determine them stably. So let O be a fixed open neighborhood of the boundary gamma. Given a fixed vector field W1 infinity, we assume that Q in L infinity of omega and its sober norm is less than M. We assume also that V in W1 infinity of omega such that its sober norm is less than M and V is known in the neighborhood of. So under the spectral asymptotic spectral condition, we have that the curl of B1 equals to curl of B2. Moreover, the potential Q and the vector field B can be stably recovered by the limit shift lambda 1 minus lambda 2. And moreover, if we assume that the following asymptotic spectral data, so here if we assume that the limit shift of lambda 1 minus lambda 2 goes to 0, and this series is converged, so we have B1, or we have the uniqueness, so B1 equals to B2 and Q2 equals to Q1. So the proof of the stability results is divided into 3 steps. First, we need to relate the Neumann data of the solution to the spectral data. Second, we will see what happened of the coefficient BHQ when the spectral data goes to minus infinity. And finally, we will relate the potential Q and B from the spectral data, and this is called the Suzuki asymptotic representation formula. So let's begin with the first step. We consider here the form perturbed Biharmonic operator here with L equals to 1 and 2. So for F in this product space and if lambda in the resonance set, this boundary value problem admits a unique solution in each part of omega, given by this representation here. And moreover, for any neighborhood of the boundary gamma, we can prove that by Lebesgue-Dominant theorem that L2 norm of U plus L2 on omega minus O of lambda U goes to 0 when lambda goes to minus infinity. And so since we have the well-posed of the direct problem, so we may define the following operator called the Dirichlet-Neumann map, which maps F to the Neumann data of U. So as I said before, the first step is to relate the Neumann data U to the spectral data. In the other words, we want to relate the Dirichlet-Neumann map in terms of the spectral data as like this representation. But here, since this series is only converged in L2 omega, so we cannot deduce it directly. So to overcome this difficulty, we use the strategy given by Kavian and al. So if we pick eta, another spectral parameters in the relevant set of H, so we assume that the expected result is true for the difference Neumann data of U associated to lambda minus U associated to eta. So the proof of this lemma is quite simple. Here, since the difference U associated to lambda minus U associated to eta solve the following boundary value problem, and since this function is in L2 and lambda is the resolvent set of H, so we can write this function in terms of the resolvent of HL applied to this function. And by using the spectral theorem, we get the following representation here. Now we use the first lemma to express U in terms of the spectral data, so we get this representation here, which is converged in L2 omega. Now we want to prove that this series converge in each part of omega. So we know that W is in the domain of H, and HW can be written in terms of U and W. So we get that HW equals to this, and then we can, which is converging L2 omega, and then we can prove that this series is converged in the domain of H. And now since the Neumann trace is continuous, so we get our result. Once we have that, now we will see what happened when eta goes to minus infinity. So let B1 and B2 and W1 infinity for omega such that B1 equals to B2 in the neighborhood O, and let Q1 and Q2 in L infinity for omega. So for even this product space and for eta is in the reservoir set of H1 and the reservoir set of H2, so we have that the two solutions U1 and U2 are closed when eta goes to minus infinity. In fact, this lemma claims that the values of B and Q is dimmed when the spectral parameters goes to minus infinity. And this is the proof is based on the result given by Kian for the Schrödinger operator. So to prove this, we consider U1 the solution U1 minus U2. We solve the following major value problem here. Since this function is into omega and eta in the reservoir set H1, so we can write W1, the function W12 in terms of the reservoir of H1 applied to this function, and so we get that the principal norm of this function is less than the into norm of this. And here, since we have assumed that B2 equals to B1 on the neighborhood O, so this the into norm of the H is less than this. And by using the first lemma, this term goes to 0 when eta goes to minus infinity. Now, once we made that, now we want to relate the coefficient P and Q in terms of spectral data. So in 1989, Isozaki introduced a simple representation formula for the Schrödinger operator. So we should relate the potential of the Schrödinger operator in terms of the spectral data. So he considered the following value problem here, with energy here is lambda tau squared. Lambda tau is given like tau plus I, with tau is the large parameter. So since this boundary value problem admits a unique solution, so we may define the following Dirichlet Neumann, which maps phi to the Neumann data of U. And we also define the following fraction, which is equal to Dirichlet Neumann map applied to the first test fraction, product scalar the second test fraction. And he proved that with suitable choice of V1 and V2, the Fourier transformation of Q1 minus Q2 is the behavior of S1 minus S2 when tau goes to plus infinity. So our idea is to extend this strategy to the Biharmonic operator. So let xi be fixed in array and tau be a large parameter. We set here lambda tau equals to tau plus I. Our idea is to look to two solutions, P1 star and P2 star, satisfy the Biharmonic operator with energy E as lambda tau power of 4, such that their product converge to this exponential time suitable function J, and they are uniformly bounded. So to do this, we pick omega in this field such that psi are orthogonal to omega, and we define omega L equals to this. So this model equals to 1, and we define rho L equals to lambda tau omega L. So if we choose P1 star equals to this exponential, it's clear that this P1 star satisfies this Biharmonic operator, and we choose P2 star equals to this exponential times this function A2 to be chosen later. Now we consider the following major value problem here. With here the Dirichlet data is the Dirichlet here is the boundary value is the Dirichlet data of P1 star. Now since UL minus P1 star solve this boundary value problem here, so we can write UL minus P1 star equals to the reservoir of HL applied to this function. And by using the reservoir estimate, the edge-norm of this function goes to 0 when tau goes to plus infinity. So here the idea is, if we prove the boundary value problem by the first test function, the solution itself behaves like the first test function when tau goes to plus infinity. Now we define the following function here. SL equals to Dirichlet Neumann map applied to Dirichlet data of P1 star product scalar the Dirichlet data of P2 star. I recall here P1 star equals to this exponential and P2 star equals to this exponential times A2. So by some computation we can prove that S1 minus S2 can be written in terms of B and Q. And with a small term here I, with I is less than the H1 norm of A2 over tau. So now the next step is to choose A2 suitably to get an information about B and Q. So our idea is to choose A2 in the following form, which is equal to alpha 0 plus alpha 1 over lambda tau r, with alpha 0 and alpha 1 satisfy some transfer equation to get that this exponential times A2 satisfy the Biharmonic equation. So first we choose A2 equals to 1, which means that alpha 0 equals to 1 and alpha 1 equals to 0. So we get that the Fourier transformation of curl of B2 minus B1 is the behavior of S1 minus S2 over tau, when tau goes to plus infinity. Moreover, if we choose again A2 equals to 1, but we assume that B2 minus B1 is Laplacian of psi with psi some function, so we get that the Fourier transformation of Q2 minus Q1 is the behavior of S1 minus S2 when tau goes to plus infinity. Now we choose alpha 0 equals to this and alpha 1 equals to this, and we assume also that B1 minus B2 is nabla of psi. So we can prove that the behavior of S1 minus S2 when tau goes to plus infinity is the Fourier transformation of Laplacian of psi plus term here in Q. Now to conclude our stability estimate, we need to study the behavior of S1 minus S2. So let eta the reservoir set of H1 and the reservoir set of H2. We define Wn is the difference of U associated to lambda minus U associated to eta, and W12 is the difference of two solutions associated to the same spectral parameters. So by some computation, we can write S1 and minus S2 like this. So here, since we have proven that the two solutions are close when eta goes to minus infinity, so this term goes to 0 when eta goes to minus infinity. So we know that f1 minus f2 is the limit of this term when eta goes to minus infinity. And since we have we have a representation formula for the Neumann data in terms of the spectral data, so we can write this term in terms of spectral data. So in conclusion, we can prove that the S1 minus S2 over tau when A2 equals to 1 goes to 0 when tau goes to plus infinity, and moreover the limit of S1 minus S2 for A2 equals to 1 is less than the limit of lambda 1 minus lambda 2. And for A2 equals to this, we can prove that the limit of S1 minus S2 is less than model of psi power of 4 plus 1 and uh, uh, the limit shift of lambda 1 minus lambda 2. Now by using lemma 9, we can this term is equal to the Fourier transformation of curl of B2 minus B1. So we get that curl of B1 equals to curl of B2, and then by Hermann's lemma we get that B2 minus B1 is the nabla of psi. Moreover, since we have proven that B2 minus B1 is the level of psi, so we can use lemma 10 and we get that this term is the Fourier transformation of Q2 minus Q1. And since we have an estimate for the Fourier transformation of Q1 and minus Q2, so we can estimate its H minus 1 norm. And finally, by using the stability estimate for Q2 minus Q1 and by using lemma 11, we get the stability estimate for B2 minus B1. Thank you.